Hi, first graders. Happy Monday. A few weeks ago I was talking to Olive for our weekly check-in, and she shared a super funny joke with me, and she said I could share it with the rest of you on our morning message. So here's the joke from Olive. Why did the cookie go to the doctor? Because it was feeling crummy. I just thought that was a good one. Thanks for sharing that, Olive. Well, today is the day that you can go to Nevlin to pick up your final distance learning packet. In this packet, you are going to find most of the things from school. So anything from your toolbox that is being sent home for the school year, your name tag, anything that was left in your mailbox, that will all be sent with this pickup. So if you are able, try to go to Nevlin today between 11 and 3:30 to pick up your next distance learning packet. Let's go on to our morning message. Dear first graders, today is Monday. Today you can go to Nevlin to pick up your final packet of distance learning materials. You might have to rewatch the video later once you have your math materials with you. Have a magical Monday. Love, Mrs. Baker. Please remember to go on Seesaw if you are able to make corrections to this note. We're going to start our math time today with a story, and as I'm reading, I want you to think about what we might be talking about next in math. So, how do you know what time it is? By Robert E. Wells. Do you already have a clue, first graders? Time is a mystery. You can't see it. You can't hear it. You can't catch it in a net and put it in a jar. But you know time is real because you can sense it passing by. In a way, time is like the wind. You can't see the wind, but you can see what happens when it blows. Kites fly in the air, clouds move across the sky, and boats sail over the water. This kind of reminds me of that story, Where Does the Wind Go? Does this remind you of that story we read earlier this year? And you can see what happens when time passes. Blossoms turn into apples, cubs grow into bears, and caterpillars become butterflies. But time is more mysterious than the wind. It is so mysterious that even the greatest thinkers and scientists can't say exactly what it is. Even so, it's a mystery we can measure. Not with a measuring tape, of course. That's what you'd use to measure an alligator. Or that's what we were talking about the last couple weeks in math. A clock can measure time. But once there were no clocks. You couldn't just look on the wall or look at your watch or look at a cell phone to tell what time it is. Long ago, people measured time with the sun. By observing the sun's position as it moved across the sky, early people could tell how much time they had to gather food or firewood before darkness returned. Our ancestors didn't know why the sun kept appearing and disappearing. They didn't understand that, as we do today, that Earth is round and turns like a top. So the world is light where it faces the sun and dark where it faces away. After a while, people invented simple time measuring devices. Egyptians made shadow stick clocks. As the sun moved across the sky, the stick's shadow moved around on stone markers. At night, they used water clocks. Water dripped from one pot to another pot with marks inside to measure the time. So as it got later in the day, the bucket would get more full of water. Egyptians were among the first to divide time into hours. These pages are kind of tricky to turn. In Europe, sundials measured hours more accurately than shadow sticks, and sand glass measured time with falling sand. Falling weight turns clock gears. By the 1300s, the mechanical clock measured time with gears and weights. Oop, I read that out of order. So now we read falling weights turn the clock gears, and escapement device rocks back and forth, allowing gear to move one tooth at a time. Early clocks had hour hands. They could not measure minutes accurately. Later, pendulums were added, so each swing of the pendulum allows the gear to move one tooth at a time. When a pendulum swings back and forth, its regular rhythm controls a clock's speed almost perfectly. With pendulums, clocks can measure minutes and even seconds. Today, quartz crystals make even small timepieces more accurate than the best pendulum clock. Atomic clocks now keep Earth's official time. While the sun helped early people measure a day, the moon's changing shape helped them keep track of months. In Egypt, the regular flooding of the Nile River was very important because the water brought new soil to the fields. Egyptians began to keep track of time between new moons to help them predict when the next flood would come. Long ago, people didn't know why the moon changed shape. Today we know why. As the moon orbits or travels around Earth, it's always half lit by our sun as shown. But from Earth, we see the light from different angles, causing different shapes. It takes about 29.5 days for the moon to change through all of its shapes as it orbits once around the Earth. We call that the moon cycle. The Egyptians saw that about 12 moon cycles passed between each flood. They made lunar calendars. Lunar means moon. Dividing the 12 moon cycles into 3 seasons: flooding, planting, and harvest. But soon they discovered they had to add extra days to the calendars because 12 moon cycles are 11 days shorter than the cycle of the seasons, or 1 year. What 4 seasons do we recognize, first graders? Winter, spring, summer, and fall. A little bit different than the Egyptians. The Egyptians didn't know why the moon cycles didn't match the seasons. Today we know that our seasons are not measured by the moon, but by Earth's orbit of the sun. As Earth travels around the sun, it revolves on an imaginary line called an axis. Earth's axis is tipped at an angle. This causes part of the Earth that's tipped toward the sun to be warmer, and the part that's tipped away to be cooler. The changing amount of sunlight causes the changes in our seasons. It takes about 365.25 days for Earth to orbit the sun. We call that a solar year. Later, the Egyptians began to use a solar calendar. They knew that the star Sirius always made its first appearance in the morning sky just before the floods, so they chose that day to begin each year. Since Sirius is in this position only once during Earth's orbit, the new calendar measured the year at 365 days, just a quarter of a day short. During the rule of Julius Caesar, the Romans began using the Egyptian solar calendar. In 46 BCE, Caesar added a leap year day to February every 4th year to account for that extra quarter of a day. Do you remember when we celebrated leap year in our classroom? That's why. Every 4 years, we make up for that quarter of a year that we didn't account for. Dude was fascinated by that. This ancient Roman calendar, with only minor adjustments and changes over the years, is the one most of the world uses now. It's off by 26 seconds a year. Today our calendar is almost perfect. With the atomic clocks, we can know the exact time anywhere on Earth. But because it's daytime on one side of the Earth, while it's nighttime on the other, you can see that because the sun's here, and it's only facing one part of the Earth right now. It would be confusing if clocks around the world showed the same time. Some people would be eating lunch in the dark. To solve that problem, our world has been divided into 24 time zones, 1 hour apart and centered on the meridian lines. With time zones, it's not the same time for everyone. Time zones usually follow the meridian lines, but sometimes zigzag around cities or countries to avoid dividing them. If you straddle the line dividing 2 time zones, it could be 9 a.m. for your right foot and 10 a.m. for your left foot. There's that person standing on the time zone dividing line. And if you're in Los Angeles at 9 p.m., you'd better not call a friend in New York for a chat. It's midnight there. So on one side of the United States in Los Angeles, it's earlier than it is on the other side of the United States in New York. Have you ever dreamed of being a time traveler? Surprise, you already are. Everyone on Earth is traveling on the path of time. The past is right behind us, and the future just ahead. Now is always exactly where we are. So far, no one has figured out a way to go backward in time, except in the movies. But if you could, what would you like to see? Do you want to see the first men on the moon, the first airplane flight, the flea collar invented, first Olympic Games, or Age of Dinosaurs? I bet that flea collar invention was there for the dog. I bet the dog would want to go back to that. Most people don't think about time very often, but it's so important. We couldn't do anything without it. Without time, nothing could move, not even a fraction of an inch. You couldn't even blink your eyes. No matter how fast you blinked, it would take a tiny bit of time. Without time passing by, you couldn't play a computer game or eat a bowl of ice cream or paint a picture or ski down a slope. How could you? All of those things take time. Aren't you glad we have time? So first graders, this book gave us a pretty good history and a good idea of time and how clocks work. We use time so often in our day, it's important that we understand how they work. So today we are going to start talking about how we tell time on clocks. All right, like our story suggested, we are switching gears a little bit today. We are now talking about time. And we are going to start by talking about time to the hour on an analog clock. An analog clock is that traditional round-shaped clock that you would think of. We have an analog clock in our classroom at school. I want you to look around your house and see if you have an analog clock at your home. Today our math pages are starting on page 589, and you can see an analog clock on the front of that page. At the bottom, it says that Robbie has band practice that starts at 3 o'clock. Show that time on the clock. The practice is over at 5 o'clock. Show that time on the clock. Trace the hands to show the time on his clock. The clock now shows 3 o'clock, the time that Robbie's band practice started. You can see that red hand is a little bit shorter than the blue hand. The red hand is what we call the hour hand. That tells the hour on the clock, and the blue hand tells the minutes. So the red hand, the hour hand, will just move from one number to the next in a given hour, but that blue hand, the minute hand, goes all the way around the clock in an hour. So that one moves a little bit faster than the hour hand. Here's how you can remember which hand is what. When you compare the words hour and minute, you can see that hour is not quite as long as minute. Minute is a longer word. Therefore, the minute hand on the clock is the longer hand. An hour, the shorter word, is the shorter hand on the clock. So again, here's that clock showing 3 o'clock. Now it says that he finished practice at 5 o'clock. Now the clock shows 5 o'clock. The minute hand is still pointing straight up to the top, but that hour hand has moved 2 hours. It has moved to the 5 on the clock. This is the time that you are asked to trace on the clock. You can go ahead and do that. When you turn to the next page, it reviews a little bit of what we've talked about. It says that there are 2 kinds of clocks, and this is an analog clock. The hour hand is shorter, and it points to the hour. The minute hand is longer, and it points to the minute. The hour hand is on the 3 here, and the minute hand is pointing straight up. So this clock is showing us 3 o'clock. You are going to look at these 4 clocks, and you are going to determine what time is shown on the clock. You are going to determine what number the hour hand is pointing to. For these activities, the hour hand is the red hand. So what number is that red hand pointing to? You can write that number on the line next to the word o'clock. On the next page, there are 8 more clocks that you can determine what time is being shown. Remember, you are determining what number the hour hand is pointing to, what number that red hand is pointing to, and then writing that number on the line. On the last page, number 13 says Ava gets home at 3 o'clock. Evan gets home 1 hour later. What time does Evan get home? In order to solve this, first graders, we have to add 1 hour to 3 o'clock. I have shown that on the paper by using this addition sentence. 3 plus 1 equals 4. We added 1 hour to 3 o'clock. And then I showed 4 o'clock on that analog clock on the right. You can do that on your paper as well. Number 14 says Roger begins reading books at 6 o'clock. He reads for 2 hours. What time does he stop? I helped you out here, first graders, and I gave you the addition sentence to use to determine what time he stops reading. He started at 6 o'clock and we are adding 2 hours. So 6 plus 2 equals what? That is the time that he stopped reading. And that is the time I want you to show me on that red clock on the right. Finally, number 15 says, Antonio tried to set the hands on his clock for 9 o'clock. Tell why Antonio is wrong. Make it right. So if you look at that clock that Antonio set, he has the blue hand or the minute hands pointing to the 9. He has the red hand or the hour hand pointing straight up to the 12. So what you are going to do is just complete the sentence that I have put on the lines here. The hand should point to the 9. Finish that sentence by writing the word red or blue in that blank. The hand should point to the 9.